the last time, right? So we know that in classical mechanics, so if you have a symmetry, for example, if you have a translation symmetry, and then the system, Hamiltonian does not depend on the position, or if you have rotation symmetry, and then the Hamiltonian does not depend on the angles, okay? And then correspondingly, you're going to have the Poisson brackets. Between Hamiltonian and momentum, or between the Hamiltonian and the angular momentum to be zero. Since the time dependent of the phase quantities are all determined by this Poisson brackets. So if they are zero, and then we have the conservation of the momentum and angular momentum respectively. Okay, and then in quantum mechanics, okay, so if you have symmetry, for example, if you have a translation symmetry, and then the potential is zero or constant. Okay, so to be more general, should be say V should be constant. Right. Okay. Or if you have rotation symmetry, and then this V does not depend on the angles. So we say this one is the central force problem. Okay. Right. And then in the first case, corresponding to the Poisson brackets in quantum mechanics, we have these commutators between the Hamiltonian and the momentum that equals to zero. Or if it's rotation symmetry, the Hamiltonian and all of this x, y, z components of the angular momentum to be zero. And of course, you also have the total angular momentum squared should also commute with Hamiltonian. Okay. Right. So this one, we have know that this is established Dirac, the correspondence between the Poisson brackets and this commutators actually was established by Dirac. Okay. And then correspondingly, we say that we can have a simultaneous eigenstates. Okay, so in the first case, we have Hamiltonian and the momentum. Okay, so that will give us the energy and the momentum. Okay, and for the rotation symmetry, we should have the Hamiltonian, the total angular momentum squared. One of the component, okay, not all of the component. This is very different from classical mechanics. Okay, so they can have different quantum numbers. Okay, so they have energy, they have angular momentum squared, and also have the z component. Okay, right. So this one we must be careful. Is that so only one component, okay? Because LC, for example, and LX equals to I Ly times H bar, okay? Which is not zero, okay? So they do not commute, okay? Right? And then remember, the energy eigenstates are stationary. Okay. So that means this kind of quantities equal to 0, or if for the case of notation symmetry, you have this one equal to 0. Okay. Right, so that's the relation between the symmetry and this conservation loss. In between is the mathematics, say that we have commutable operators, so that we have this physical quantities can have simultaneous eigenstates, right? Especially one of these physical quantities is Hamiltonian, so the eigenstates is stationary. So if it's stationary, that means the angular momentum and all the momentum will be time independent. All right. So now we're going to apply this theory to the central force. Okay. Right. So in this case, the potential depends only on the distance on this one. Okay. So the Hamiltonian that can be written as minus h bar 2m right? So this is the Laplacian, and then plus the potential, okay? And obviously this one is independent of the angles, right? So it's intriguing to use the spherical coordinates. Okay. So the differential, of course, is given by okay. So we can do the transformation and to replace this xyz with I sin theta cosine theta, right? So in this spherical coordinates, the Hamiltonian becomes something like this one. So there will be the differential only with respect to the this radius, okay? But you also have a term okay, you have a term because relate to the angles, right? Okay. And plus the potential, okay. But these angles, so if you look at this one, these angles actually are related to the angular momentum operator squared. This one equals to minus h bar squared. And there will be two terms. So this one is basically the differential with respect to the angles. Okay. Okay, so in this case, so using this one, so you can actually write down the Hamiltonian, you know, like this. Okay. And then you have one term that's related to the angular momentum. Right? And plus VR. So you can see obviously you have the Hamiltonian commute with the angular momentum squared. Right? Since the angular momentum squared only operate on the angles, and the Hamiltonian has either the angular momentum or the radius, right? So that means if you are acting L, you know, after the Hamiltonian, so you will not change the radius. So that means these two are commutable, right? Okay. And furthermore, if you look at this L squared, that equals to minus h bar squared. Sine theta, partial theta, and sine theta, partial theta. And then minus h bar squared, partial phi squared. So you can check this term. This term actually is nothing but just the LZ squared, right? The LZ equals to h bar alpha I partial phi. So that means LZ squared is nothing but just h bar squared. There's minus partial squared, partial phi squared, right? So we obtain the so this total angular momentum can be written as partial squared 1 over sine theta partial theta sine theta partial theta plus LZ squared. Okay, so you can guess. Oh yes, sorry. There's sine squared theta. Thank you. Right. So this part only contains theta, and LZ only acts on phi. Okay. So you can say that similarly, you must have. Sorry. Let me check. Yes, I think it's right. So you have L squared, LZ commutes. Okay. And of course, you also have the previous one, right? The Hamiltonian commutes with L squared, and also Hamiltonian commutes with LZ. Okay, right? So that means we can have simultaneous eigenstates of the Hamiltonian and the total angular momentum squared. Okay, and the LZ, the Z component, right? So that's what we have done before. Okay, but we can actually work this one using a more mathematical way instead of using these symmetry arguments. Okay, so you look at the Schrödinger equation. Okay, let's look at the Schrödinger equation. So we want to find the eigenstates of the Hamiltonian and to try to form this one also as eigenstates of the angular momentum. Okay, right. So you can see that this Hamiltonian is going to be minus h bar squared over m squared, 2m, 1 over r squared partial r, r squared partial r, and then plus 1 over r squared. And these are the L squared, right? Now you can have the wave function equals to this wave function. Okay, this expression is a function of theta, r theta phi. R theta phi. Okay. All right. And now this one is a differential operator on theta and phi. Okay. Right. So we can try to write this per psi as a function of r times another function, let's say y, of theta and phi. Okay, we do the separation of variables. Okay, so the reason is that you can actually separate this one into two, this operator into two parts. Okay, so the motivation is that you can change this equation. For example, you can change this equation into, say, E times R squared minus, so plus H bar squared over 2M. Okay, partial R, R squared, partial R. Okay, right. So this is the only thing that contains on the this variable R, right? That equals to L squared, per psi. So this one only acting on theta and phi, and this one only acting on R, right? So that's why we can write down this one into two parts. Okay, so basically, the left-hand side is actually on R, right? So if we do the separation of variables, so you can replace this one with R times Y. This one is R times R, right? And now you can divide R to both sides. So on the left-hand side, you can divide this one. So you got a Y right here. R right here. You got a Y right here, right? You divide both sides by Y times R. Okay. Maybe this is a little bit messy. Let me try to redo it. Okay. Right. So this is y r times y. Okay. And now you divide the ry on both sides. Okay. So you obtain an equation. So then you basically divide on both sides. So you divide the ry right here, ry right here, right? But you know that this operator does not act on y, so this y can be cancelled. It can move outside, right? And this one does not depend on theta, so you can move this one away. So now you can see that the left-hand side is a function of r. The right-hand side is a function of theta and phi. So it looks like there's some internet connection problem. Right? I'm using another computer, but this computer doesn't have a writing system. Let me check the. So sorry about that. Please wait for a few minutes. So let me fix the internet problem. Okay. So from which part did you lose the internet connection? So I need to go back to. Okay. So I will just roll it back a little bit. Yeah, so we are back. Okay. Yeah, sorry about that. It's messed up. Okay, so let's look at this. Sorry, there's something that I messed up. So there should be plus the potential, right? So here you should minus the potential. Of course, this doesn't change the results, but we need to be careful. And there's a minus sign right here. Okay. This plus minus sign, yes. And over 2m, I think. So let me redo this one in case you missed this. Okay. So let's do this differential equation. So this you have this kinetic energy part comes from the all right, and you also have another term that is r squared times 2m, and then L squared, right? You have also the potential, of course. And this one acting on per side should equals to E times per side. Okay? And you can see that this part contains, only theta and phi. And this one is the angle, right? So, sorry, it's the radius. But then you can multiply radius squared to both sides. And then you can obtain a simpler equation, okay? So you got a 2m r squared times E, okay? And then plus h squared over the h bar squared, partial r, okay? And r squared, partial r, right? So basically times this factor to both sides, and then move all the terms related to r to the left-hand side, and the per side, right? So that equals to L squared acting on per side, okay? And obviously this one acting only on theta and phi, and this one acting only on r, right? So that motivates us to separate this one as r times y theta phi. So you replace this one with r times per side, sorry, y theta phi, right? Okay. And then you can divide the r and theta to both sides. So on this one, you can have r and y. This one you can also add r and y. Okay. But it seems this r is a function of r. So the angular momentum has no effect on that. So it can be moved out of this operator. Okay. And similarly, this one is a function of theta and phi. So that one can cancel this one, right? So basically, you go to the left-hand side. Oh yes, thank you. So there's a factor. Yes, you're right. Okay. And there's a 2m r squared right here. Okay. Yeah, you're right. Thank you. So the left-hand side is a function of r. The right-hand side is a function of theta and phi. So you have no choice. So they must be equal to the same constant. Right. Okay. So that means for the separation of variables, okay, so set I theta phi written as a function, a radial function of r, and an angular function of theta and phi. Okay, so you obtain the two equations. So one is 2m r squared times the energy E, and then plus h bar squared partial r, and r squared partial r, minus 2m r squared VR. Okay, and this r should equal to a constant. Let me call this constant L and L plus 1 h bar squared and r. And also we have L squared. Sorry. Divided by r equals to constant. Okay, and this divided by y should equal to constant. Okay, so this one has a dimension of L squared, right? Okay, so to make sure, so L is called an angular quantum number. Okay, that's to be determined. Okay. So this one, let's look at this one first. So this one, we got two things. First, it depends on V, R. Okay. So if you change the VR, you got a, so each VR gives a different Schrodinger equation, right? Okay, for the radial part. And also, secondly, it depends on L. Okay. So each L gives to a different. Okay. For this reason, you can write down this as a function of ML. So because the eigenvalues and eigenstates of the first equation actually depends on the result of the eigenvalue of the second equation. Okay. And then this radial part, okay, can be written as L squared y equals to L plus 1 h bar squared and the y. Okay, so you can say that this is nothing but just the eigenvalues of angular momentum squared, right? Okay, and we wish to solve the general central force problems without referring to the specific form of this potential, okay, at this stage. So for the general features, okay, so you can see that so all different central force problems that has different VR, right? they share the same features of Y, theta and phi. That's eigenstates of this right. So to study in general the features of these central force problems, we wish to understand this eigenstates of the total angular momentum first, okay? And then we can, once we have obtained the eigenstates and eigenvalues of the total angular momentum, and then we can put this one back to the radial part, okay? So once L plus 1 h bar squared is known, okay, and y theta, we can put the L right here, phi is known. Right, so you can put L right here to indicate the eigenstates. So we can, so the radial Schrodinger equation now becomes minus h bar squared 2m r squared partial r and r squared partial r. We just recover that one, right? And then you have for L plus 1 and h bar squared over 2m r squared and then plus VR. So this one, we give the energy M. But remember, this one depends on L, right? That depends on, so you have another index that depends on L. And R, and also depends on L, R, right? So you can see that for all the states L, okay, E, M, L are the same, right? Sorry. So each L gives a new Schrodinger equation, okay? So the number of states with the same L that will have the same is the number of energy degenerate states, right? Okay. So, you can so these are the general features. So we solve the eigenstates eigenequation for the angular momentum. We find the states YL with the angle with this quantum number L, and then we put this back into the radial part of the Schrodinger equation, and then we got a new Schrodinger equation for each L. Okay, so that will give us the energy E and L. Okay, and if there are more states that have the same L, and then there will be more states that have the same energy, right? So you can see that the number of states that have the same eigenvalue of the angular momentum is actually the degeneracy of the energy. Okay, right. So from this one, immediately you can see this this feature. Okay, right. Okay. All right. So now let's try to solve this equation. Look at this eigenvalue problem. So that is L squared and y L theta and phi equals to L times L plus 1 h bar squared y L theta phi. Okay, so this one we just put back this, right? So that's minus h bar squared 1 over sine theta partial theta sine theta partial theta plus 1 over sine squared theta partial phi squared. Okay, y L theta phi equals to L plus 1 h bar squared y L theta phi. And now you can see that again, this one only acting on phi, right? And this one acting only on theta. So we can do the same thing. We can actually separate again the variables of theta and phi. And we write this y theta phi as a theta function of theta and a phi function of phi. Okay. So follow the same procedure. You can see that we can have the equation okay. So once if this one is nothing but just LZ acting on phi, sorry, equals to m h bar and phi, right? And then you put this back into the one, so you got another equation that is minus h bar squared, therefore sine theta partial theta and sine theta partial theta and plus 1 over sine theta partial phi squared. But now remember this one, we just give you this eigenvalue, right? So that is nothing but m squared. Okay. Times h bar squared. All right. That's square. And the y theta and phi equals to L plus 1 h bar squared and the y L theta. Okay. So now in principle, since this one depends on m, so this one should also depend on m. Okay. Actually, if you look at furthermore, even this one should also depend on m. Okay. So you can actually put m right here. Okay. So the eigenvalues of this one should also depend on m, right? So we got a two set of equation. So once you got the eigenvalues of LC as m h bar, and then we can put this m back into this differential equation, the Schrödinger equation for the theta part. And then from that part, we can, sorry, this one, we have separate variables. So we got this equation on theta, right? L, this in principle should depend on m. Okay. Okay. But once you have obtained the eigenvalues of the angular momentum in the z direction, m h bar, and then you can put back this into this equation, right? And then you can got a new. So each m gives a different Schrödinger equation for theta, right? So you got a new eigenstates and new eigenvalues, okay? And then from that one eigenvalue, you put back to the radial part, you got the total equation, okay? So we do the separation. So if you, so we do the separation. So we go to I theta phi change to I and the theta phi, right? So this is per psi, this is R, this is Y. And then furthermore, this one change to be, theta and the phi, we separate them. Okay, so we keep this separate, this one. And from this one, once you obtain this, this got M H bar, right? And then you put it back to this one, you got a LM plus 1 H bar squared. And then you got the equation, for the R, M, L, M, right? So you do a separation, from 3 to 2 and 2 to 1, okay? And then you got this eigenstates and eigenvalues for the phi components. And then you put back to the theta components. And then you put back to the R components. So this way you solve the equation, right? And the phi component is actually very simple. So it's H bar Fi partial phi, and the phi equals to M H bar and phi M phi, right? And obviously this equation is, the solution is okay, right? But M cannot be arbitrary because there is boundary conditions for wave function. Okay, so in this case, so you change this phi. Okay, so you must have phi M0 equal to phi M2 pi, right? So that means M must equal to integer numbers. That's 0 or plus 1, plus 2. Okay. So you obtain, one solution, obviously, right? And then the next one is you just put back to this one, so that way you got the equation to be minus H bar squared. Okay. That way 1 over sine theta, partial theta, sine theta, partial theta, right? And then you have this term, right? That comes from the, the solution of the phi component. Okay, this acting on the theta function. That should equals to, for example, L plus 1 H bar squared, the theta and the theta. Okay, so this one depends on M, of course. So the question is, okay, and L equal to what? Right. So let's take a break, and then we can just come back to this equation and to solve it. Okay. Okay. So we'll try a serious solution again. Okay. And you can see that we have very few methods to do this kind of differential equations. Usually it's not easy. So unfortunately for this one, we do have a solution. Okay. First of all, we easily you can divide it by H bar to both sides, right? Okay. So but we can do a change of variables, we can define u equals to cosine theta. Okay. And with this one, you can say that partial u will equals to partial theta partial u times partial theta, right? Okay. So that means partial theta equals to partial u partial theta. And partial u, right? Okay, so that equals to let's say partial u minus sine theta. Partial u, right? Okay. Or in other words, you have 1 over sine theta partial theta is equal to minus partial u. Okay, so that means you can change this one to be just partial u. Okay. Okay, so the result is you change the differential equation to be minus partial u. Okay, and now this one will be sine theta is going to be minus u squared partial u. Okay, and minus m squared 1 minus u squared. Okay, equals to L times L plus 1 times acting on theta, sorry, and equal to theta, right? Okay, and now we can write this as u, as a function of u. Okay. All right. Let me copy this one to the next slide, or maybe just move on. Okay. Yeah, here. And change this one a little bit. Let's say. Okay. So this one is give us the first one is a partial squared, partial u squared. That's the first term. And the second term will give you plus u squared, partial u squared, right? And then you have one more term that is plus 2u, partial u, right? Okay. And then plus m squared, 1 minus u squared. And theta u equals to L plus 1 theta u. Okay. Let me check once more. So this one acting on this one that give you this term, and then I think it's right, right? Okay. And this one is in general can be solved, but let us consider a simple case first. Consider the case m equals to 0. So this is the simplest case, and then the equation becomes minus partial squared, partial u squared, plus 2u partial u, plus u squared, partial u squared. Okay, acting on this theta. And now to denote this special, we call this one PL u equals to L plus 1 and the PLU. Okay. Right. So let's write down this PU as a series. Okay. And then just put this back into the differential equation. Okay. So you can obtain that if you look at the check the terms, that's check the coefficients of u to the power m, for example. And then the first one will give you minus m plus 2, m plus 1, a m plus 1, right? And the second will give us plus 2, m plus 1, and a m plus 1, right? Is that right? Sorry, a m. Okay. Right, and then the third one will give us m minus 1, and am, right? So that will equals to l plus 1 am. Okay. So if you combine all of these terms, you find that you got an iteration equation. Okay. And this one will give us m plus 2, m plus 1. What will be this result? 2m n squared minus m. So what's this? This is n squared minus m plus 2m plus 2. So that equals to m squared plus m plus 2. So this will give us m plus 1 times m plus 2 minus m times l plus 1, right? Is that right? I hope I didn't make a mistake. Let me check the notes. Looks like I made a mistake somewhere. Oh, sorry, this is 2m. Yeah, I know where's the mistake. This is 2m. Okay, so this one is m. Okay. All right. So you can see that supposedly, so if m goes to infinite, you find that this am plus 2 will just be, you know, am, right? The same order. So that will lead to pu divergent at u equals to plus or minus 1. So if u is less of, you know, than plus or minus 1, it will be okay. But the u could be 1, right? So what means u? So remember, u equals to cosine theta. So u equals to plus or minus 1 means theta equal to 0 or pi, right? So that means, so this one will lead to divergent wave function at the north or south poles. So that's not physical, right? Unless the series terminates somewhere, right? So how can this one be terminates? So the only possibility is that L equal to 0, 1, 2, all non-negative for integer numbers. So in this case, you can say that so when you increase m at a certain point, so you will immediately got this one to be 0, okay? So once n equal to L, so you can find that AL plus 2 will equal to 0. Okay, and AL plus 4 will equal to 0, and so on and so forth, right? Okay, so this is one thing. Okay, and secondly, you can see that this P L theta LU, sorry, should be either odd or even function of U. Because you can see that the coefficients, this AM plus 2. So that means you must have either start from the zeroth order term. You got A0 and A2 and A4 and then terminate. Or you start from the A1. If L is odd number and you have 1, 3, and 5, 7, so on and so forth, and then terminate when n equal to L, right? So that means you cannot have a mixture of odd or even functions to be the eigenstates. So you can see that once again, the important thing is that so the physical boundary conditions on the wave functions leads to quantized L squared that equals to L plus 1 H bar squared, and L equal to 0, 1, 2. That's the only possible numbers. Okay, so this is one thing. Okay, and there's a solution. PLU has a name. It's called it's a polynomial, right? Lagrangian polynomial. Okay, and the L means the Lth order. Okay, so you can easily just do this one by by the series solution. Okay, and then I just give you the list, a few examples. Okay, so P0 U actually is just a constant, right? Because if L is 0 and then the next term already terminates, right? So you cannot have more than 0th order terms. Okay. And then the first order term is P1 U. Of course, that should be U, right? Because it terminates immediately after the first order term. Okay. Okay. And the P1, P2 U, that will have 2 terms. Okay. So in principle, you can start with 1, but by convention, we write this one as a constant 1 over 2 square U square minus this one. Like I said, this one should also you cannot have higher than this order terms, right? And the P3U equals to 1 over 2 5U cubic minus 3U. Okay, so this one should also terminate at the fifth order term, and then P4, of course, we have 3 terms. You don't need to remember this one. Okay, nobody can remember this one unless something is extremely obsessive. Okay, just write down a few terms to let you have this one. Now remember, the U is defined as cosine theta, and the theta is in the range of 0 to pi. So U changes from is in -1 to 1. Okay, so that's the range. Right. So this is a few examples of this one. So if we plot this Okay, actually, so this is P0. Okay, that's a constant. And then the next one, we actually will be, this is P1. Okay, and then the third one, will be an even function, right? Okay, so this is P2. And all of this one, actually, the coefficient I chosen so that PL plus minus 1 equals to, plus or minus 1 to the power L. Okay, so this is for the coefficients chosen, okay? Right. And there is also some other properties of these functions. And also you can see that, it's an even function for the even order, and the order function for the odd order, okay? But this is a zeros, okay? Right? And the P2 has 2 zeros, right? P1 has 1 zeros, and the P3, you're gonna have 3 zeros. P3 is it should be something. Let's say P3 should be something goes like this one. It's bad drawing, but you know what I mean, okay? So this is P3. Right, so you can check internet or the next notes for more cases, okay? Right, so we obtain the solution. Basically, for m equal to 0, we have L equals to 0, 1, 2, and so on and so forth. And the solution is phi m just equal to 1, and the PLU just equals to theta L cosine theta just equals to PL cosine theta. Okay, so we write down this. The y now has 2 index that equals to that basically equals to PL cosine theta EI0 times phi, right? So divided by certain kind of normalization factor. We will come back to this one later, but this is just a normalization factor, okay? Now the question is, how about the m is not 0? Okay. You can try the solution again, okay, but it's more complicated. So we will not do this. So the equation now can be written as you got an equation that is minus d over du 1 minus u squared d over du, and then now you have this extra term, right? So this obviously gives you more trouble. And the solution, we also denote this one as PL mu, that will equals to LL plus 1 and the PL mu. Okay, so let me just give you the solution. Write down the solution immediately. Okay, so basically this PL mu is called a associated Legendre functions. Okay, they are not a polynomial. Okay, in general, that's the first thing. Secondly, to make sure PLM plus minus 1 is not infinite, okay? And this L must equal to at least the absolute value of M, and then M plus 1, and then M plus 2, and so on and so forth. So once again, the physical boundary conditions leads to contest L, like this, right? And the third thing, of course, PL0 U is nothing but just PL U, right? Okay. And the PLU actually has a definition in terms of can be generated by this differential operation. Okay. But so you can see that so this one, so it's a Lth order polynomial, right? Okay. And PLM can be generated from the PLU. Okay. Now you do this one to M's order, to L plus M's order. So from this one, immediately you can see that M must be less than L, right? Or equal to L. Otherwise, or PLM will be 0. This first thing, right? Because you need to do this one for L plus M times. And also, it's not a polynomial. Because if you look at this term, this one basically is square root of 1 minus cosine squared theta, and then to the power m, right? So that equals to sine to the power m. Okay. So you can see that this one is not a polynomial of u. Okay. But it contains sine theta, right? Okay. A few examples are given in the lecture notes, okay, and also you can easily search this one in the internet these days. Okay. But anyway, so let me give you a summary of the solution. Right. So the solution is L squared and the y Lm theta phi. That can be written as L plus 1 y L theta m, sorry, theta phi. Okay. And this is also a function, eigenfunction of that's h bar squared, sorry. Okay. Right. An important thing, so the physical boundary conditions, basically is that y does not equal to infinite. Okay, when these two m, for any m equal to 0, plus minus 1, plus minus 2, and so on and so forth. For each of this one, L must equal to m plus 1, m plus 2, and so on and so forth. So this is important. Or you can write this in a different way. You can say L equal to 0, 1, 2, 3. And then m equal to 0, plus minus 1, plus minus 2, and so on and so forth, plus minus L, right? That means for each L, 2Lm theta phi with m equals to 0 plus minus 1 plus minus 2 and then plus minus L. There are 2L plus 1 states of the same value of this one, right? Same eigenvalue. Okay. So that means EML has degeneracy of E equals to 2L plus 1. Okay. Right. Since the eigenstates M, L, M equals to R, M, L, R, and Y, L, M, theta phi. Okay. So this Y, L, M, theta phi, okay, is called a spherical or harmonics. We will see a few more examples. Harmonics. Okay. So it has the form. It's P, L, M, cosine theta. Okay. Times e to I m phi. Okay. Divided by constant. That's 2 to the power m and 2 to the power L. And let me be careful with this. But this is just normalization factors, okay? You don't actually really need to memorize any of this. Okay, so if you really want, it's minus 1 to the power m, and then there's square root 2L plus 1 over 4 pi, and L minus m factorial to L plus m factorial. Okay, never mind. Okay, we don't need these coefficients. So this one is called associated Legendre functions, okay, or Legendre polynomials for m equals to 0. Okay, this is for m is not 0, and this one, of course, is just LC EIM phi that equals to m h bar EIM phi. It's just eigenstate of the right. So you can say that it's almost like a plane wave on the. No, so you can say that if you draw a circle, okay. So this function just also like this one, right? It's by join. Anyway, so you know what I mean, right? So that's the say this is the real part of EIM phi. Okay. All right. So why we call this one spherical harmonics? Okay, so it has two terms. One is harmonics. Secondly, it's spherical. So what does this mean? Okay. So what's harmonics? What's harmonics? Like for example, if you have music, so you have a C, and then you have a high C, C1, say for example, and then you have C2, and so on and so forth, right? And this will give you actually you know, harmonicas, right? Okay, so you can have a function, for example, f t that equals summation of, you know, fm cosine m times the frequency times 2 pi times t, right? So this one is the, you know, is the harmonics. Okay. Right, so you can have this one. You can have right. You can have a summation of them. So that gives you something like a more complicated. Okay. Whatever, right? So you can have a summation of all these kinds of harmonicas. So that will give you still something periodical, but it could be more general patterns. Okay. And all of them is spheric. Spherical harmonicas. Okay. So these are just standing waves on spheres. Okay. Right. So that means any vibration, any waves defined on the surface of a spherical shape can be expanded by harmonicas. So this means, so that means any function, say phi, f theta phi. Okay, so this is a wave on a sphere. Okay, can be defined as summation of Lm and f Lm ylm theta phi. Okay, so that's why this one I call the harmonics. That's the elements to form waves on sphere. Okay, right. So I have a sphere right here. Right. So this is a sphere. So you can see that. Can you see this one? Yes, great. Right. So this is a sphere. You can imagine that this sphere can vibrate like this one, right? If vibrate like this one, and then you know that in the equator, there's no vibration. So you should have. So if you have a sphere like this, okay. So if you have a sphere like this one, and this one is vibrate, and then there's no vibration. So along this equator, there's no vibration, and then you have vibration right here. So this is a wave, something like this one, right? So you can imagine that this one is something like a P, you know, to be expanded as, for example, P1 U that equals to cosine theta. So you have a large amplitude at theta equal to 0 and pi. That's north pole and south pole, right? Okay. But in the equator, 0 at equator, right? That's theta equals to pi over 2. But you can also have the expansion. You can have the wave like propagate along the. You can have another wave like this one. So that goes like this one along this equator, and then becomes smaller and smaller, and then there's almost no, and then there's 0. There's no. Similarly, you can have vibration on this one, and then this amplitude becomes smaller and smaller, and then eventually there's no vibration at all. So this one will give us something like a, say P11. That's about a sin theta, right? So 0 at poles, and the maximum at equatorial, right? So you can have different kinds of modes of vibration, okay? And then you can use this one to expand all of this one. So actually, this y Lm theta phi that was defined as minus m to the power m 2l plus 1. These are just normalization factors. L minus m to the factory and L plus m to the factory. And PLM cosine theta, and then EIM phi. Okay. So they are spherical harmonics. So first of all, they are orthonormal. Okay. So that means they're orthonormal. Okay. Now be careful with this one. This one actually means the complex conjugate theta and phi, L prime, M prime, theta and phi. It's not just d theta d phi. Okay. This sine theta d theta d phi. Okay. Be careful with this one. Okay. This is called a measure. That's because if you look at the circle, if you look at this one, the surface area actually is different for different theta, right? So this is sine theta, d theta, okay? Right. So this one is if you have this one is gets smaller and smaller, this becomes almost zero, right? So when you change the theta a little bit, the area element actually should be multiplied by this sine theta, by this measure, okay? So that's why we need to have this sine theta, okay? Later on, when we discuss the probability distribution in hydrogen atoms, we also see this kind of measure, okay? Because if you don't take this one correctly, you actually are not weighted probabilities correctly. So this is one thing, okay? And secondly, any function can be written as summation of m as L, sorry, m, f L m, and y L m, theta and phi. So that means this is complete. Okay. So and this FLM obviously can be obtained by right. So this one is called a complete. Okay. So harmonics are like this one. Okay. In the internet, there are a lot of videos and pictures showing the shape of this spherical harmonics. So now I'm going to share this one with some PowerPoint to show you some of these pictures. Okay. Okay. Let me stop sharing this whiteboard. Let me stop this sharing. Okay. Okay. Can you see the PowerPoint?
No. Yes, now.
Can you see the PowerPoint? Yes, great. All right. So now this I just show you a few examples of this, spherical harmonicas. So the first one is the one that you have L equals 0 and M equals 0. So that's a spherical, right? You know that the M is, so if L is 0, Y is 0, then both of them are just constant. So that means basically there's no vibration at all. It's just a constant, okay? Or the sphere just kind of it's not a wave. It's just expanding and compressing, right? So the amplitude is the same everywhere. And then the second line is the case that L equals to 1, and then you have 3 components for M equal to +1, -1, or 0. So if it's 0, okay, and then you have something that is so if it's 0. Okay, so if it's 0, and this one is e to I m equal to 0 times phi. So it's independent of phi, right? And then you have p 1, okay, u, and this one is just cosine theta. So that means you can have some vibration, okay, that's maximal at the loss pole and source pole with opposite sign. But it's the same along this one, so that's rotational symmetry, okay? And for this one, and this one, you have m equals to, say, +1, m equals to -1. So you can see there's a phase. So the phase, right, you have em0 equals to 1, and im pi equal to -1. So there's a phase opposite in the x direction and minus x direction. So you can see this color that indicates the phase, right? So you have an opposite phase in the x and minus x. So in another case, if m -1, you have just the phase just opposite, right? So you can see that there's a kind of this phase difference. And if you go to the case that L equal to 2, and then you have m equals to 2, 1, m equal to 1, m equal to 0, m equal to -1, m equal to -2. Okay, so you can see that the phase change. So if you go around this one, the phase change from positive to negative and then positive. So this is positive and negative, positive, and then negative. So you change the sign, 4 times. Yes, 4 times along the circle, right? In this case, this is +1. This is m equal to 1. This is +1. This is -1. So if you go along this one, the phase change once, okay? But you have more modulation in the z direction, okay? In this case, the phase is not changed along the circle. In this one, the phase is changed opposite, like this way, okay? And this one is the same, change 4 times. This change 2 times. And then you can go to L equal to 3, for example. And this one, you can see that the phase change will be plus, minus, plus, minus, plus, minus. So you change 6 times, right? And then 4 times, and then 2 times, and 0 times. Okay. So you can see the number of phase change along this polar angle defines the m. Okay. So this is one thing. Okay. All right. So this one basically show you how this phase change when you rotate the sphere. Right, so you can see that if m equal to 1, the phase only changes once if you do a field circle rotation. And m equal to 2, that's the third column. The phase changes 4 times. And then the third column, or the fourth column, that changes 6 times, and then 8 times, okay? So that's different number of times the phase change when you rotate this sphere. And see this wave function change the sign, okay? And then you look at the real part and the imaginary part, okay? So the first column, the first line is again the 0, 0. So that's spherical. So everything is constant. And then this is the one that we have shown that the phase change from now. This is +1, and this is minus. So the phase change once. And this is the real part. So the real part, you know that if you have EI phi, the real part of this one is nothing but just cosine phi. And this one is proportional to x. It's just x divided by r, right? It's proportional r times sine theta, sorry. So that you can see that, so this one is going to be in the x direction. Okay? Right, so that's for the case L equal to 1. And if you look at the L equal to 2, so if you look at this one, the phase change from +1 and the minus, and then plus, and then minus. The phase change 4 times, and this one, the phase is plus, and then minus. So you change once, right? But you can also look at the real parts. Look at the real parts, okay? The real parts is e to I 2 phi. So you look at the real parts of this one, it's going to be cosine 2 phi. Cosine 2 phi is basically just cosine phi squared minus sine phi squared. So that is x squared minus y squared, right? It's proportional to this one. So this one is also called a state x squared minus y squared. So that means if you look at this one, so it's going to be plus minus first of all. That's a sign change. But now it's along this in the x-axis and the y-axis is 0. Okay. And for this one, you can see that this one is called a xz direction. Okay, so that means so in the y-axis and the z-axis is going to be 0. Okay, so you have different shapes of this states, and you can also discuss this one. Go to higher orders. Okay. One more animation. Okay, right. So this shows the spherical harmonicas L equal 0 and M equal 0. So it's a spherical symmetrical. The sign is constant everywhere. So you can see that this one is the left one is M equal 0 for L equal 1. So you just polarize in the z direction. And then in the xy plane, actually you have 2 components, right? So if you look at the real part is in the x direction, the imaginary part is in the y direction. And then if you have one of this one, you rotate this one. This is just rotation in the xy plane. Okay. Right. So that shows the case that you have L equals to 1 and M equals to 0 or plus minus 1. Right. So this is the case for L equals to 2. And then M equal to 1 or plus minus 1 or plus minus 2. Right. So let's just show you how this one look in the 3-dimensional case. Okay. So the length of this one is basically shows the amplitude of the wave function. And then the colors shows the phase, right? And then you look at this one from different angles, in the 3D space. So this is the case that we have L equal to 3. So you can have M equal to 0, or plus minus 1, or plus minus 2, or plus minus 3, right? So you can have different kinds of sign change, right? So if M equal to 1, the sign only change once, okay? Right. So this is even more. This is for the case that L equal to 5, and then M can. So this is the L equal to 4. Sorry, the M can be from 0 to 1 to 2 and 3 and 4, right? Okay. So this one gives you a summary of all these kind of states, the real parts and the imaginary parts of this spherical harmonicas, and the color. The gray or the white colors actually shows the sign of the wave function. So you can see the number of nodes, right? So there are a number of things that you can see. Okay, so For example, if you look at the 24, right? 24 says L equal to 1, 2, 3, 4. So M equal to 4. And then look at this M actually is 4. So that means the sign will change 8 times. So you have plus, minus, plus, minus, plus, minus, plus, minus, and then plus. So the sign changes 8 times along this circle. Okay, so this is M equal to 4. Right? And also you can look at the number of nodes, right? So you can see that the planes where the wave function is 0, so there will be 4 planes like this one, and this is the same for the other states. Okay, right? So the number of planes that the wave function is 0 actually is equals to L. Okay. All right. So these are just kind of a few illustration of this these angles, okay? Of this spherical harmonicas, different angles. Okay, so you can, so we have kind of, this gallery of this states, right? So that's pretty much what we have for this central force problems. Okay. So the important thing is that we have this spherical harmonicas that can be solved. These actually are the elementary plane waves. Sorry, the waves in the on the sphere. Okay. Right. One more thing. Sorry about that. So one more thing is. So you know that these states, this is Y, L, M, they are the eigenvalues, eigenstates of the total angular momentum squared, right? And they are also the eigenstates of this MC. But you know that M is always less or equal to L. So that means LZ squared, that equals to M squared, H bar squared, will always be less or equal to L squared, H bar squared. This is definitely less than L squared, right? So that's something different from the classical mechanics. So that means you can have a state. Suppose we have Lx, Ly, and Lz, okay? And then you cannot have this one suppose equals to L. And then Lz actually is always less than L, right? So that means this one is not 0, right? Something like this one. But if you really calculate, this Lx, okay, they're all 0. This is all 0 for Y, L, M. It's very easy to check, and we have these examples in the access classes. Okay, so basically you can use you can write down this Y, L, M equals to P, L, M cosine theta, and then e to M phi. You act in this one, X on this P, Y, L, M, and then put a Y, L, M right here. You do the integration. This one is always 0. Okay. So that means, and then you have Lx, Ly, and Lc. Actually, they do not equal to square root of L squared. So the reason is that so this one squared actually equals to Lx squared plus Ly squared plus Lc squared, right? And this one should equal to Lx squared plus Ly squared plus m squared h bar squared. Yeah, this one is L times L plus 1 h bar squared. So that means immediately you got that Lx equal to Ly equal to 0, and Lx squared plus Ly squared, that equals to L times L plus 1 minus m squared and h bar squared. So this one is positive, right? And of course, we should have Lx squared equal to Ly squared, right, average for symmetry. Because the choice of x, y actually is up to your, convention. Okay? It's not really physical. So you can choose this one to be x, that one to be y, or you just change this one to be x, this to be y, right? Doesn't really matter. So this means Lx squared, that's equals to Ly squared, that equals to L times L plus 1 minus m squared over 2 times h bar squared, right? So that means delta x squared equals to delta y squared, just equals to. Okay. So this means that if we do the measurement of the angular momentum in the z direction and the xy direction, in the xy plane, you got some uncertainty. So if we measure L, okay, you got a certain LC that equals to m h bar, but uncertain Lx, Ly, right? So this means if you plot all possible values of the measurement for different states, so that will be on circle, like this one. Okay, so we use this kind of coins to, okay. So this is m equal to L, this is m equal to L minus 1, this is m equal to L minus 2. So you can see that the z component is always, so this is m equal to 0, right? And this one is m equal to minus 1, and so on and so forth, right? So you can see that the components, the z component is always less than L, or equal to L. And then you have fluctuations in the xy plane, okay? So it's because of the fluctuation. So that is something, again, important in quantum mechanics. So fluctuation of Lx and Ly makes Lc less than, right? Okay, and this kind of picture is called a so-called quantization. That's obsolete actually, but I give you some kind of way to have a picture, right, of this angular momentum, quantization of space. Okay, it's not really quantization of space; it's quantization of angular momentum. Okay, so z is certain, but the xy is uncertain. So that you have a distribution of xy, to anywhere right here. Okay, right. Okay, so that's another thing that I want to mention. Okay, for this spherical harmonic states. All right. Sorry for a little bit longer than scheduled. So any questions? Okay, how do we determine the conventional z direction when we're doing the measurement? A wonderful question. Okay. The question is, wow. Okay, actually, no way. We cannot determine what is this direction. So you just choose. Okay, you can choose this one to be the z direction. You can choose this one to be z direction. It's up to convention. You can basically choose any x to be z direction, but as long as you choose this one to be x direction, and then you do the measurement on this direction, you will get a certain. Okay, suppose you do vector of this m. So you measure the state. Okay, along m. So basically you measure m dot l. You basically got a randomly some m h bar. Right. And then you can choose this one to be call this one xm, this one ym. Okay. And then the measurement of L in the xm direction or L in the y direction m, okay, will give you random output m h bar as well. Okay, so that means no matter which direction you choose to measure, you always got a m times h bar. After you measure in this direction, then choose to measure in another direction, you still got the m h bar. Okay, along any direction, do the measurement, you always got an m h bar. Okay, so you always get a random. So if it's not eigenset, okay, a random m h bar. Okay, along any direction. So you can say any direction is the z direction. Okay. All right. But there is one thing. But L squared is always L plus 1, h bar squared. So if you have a way to measure L squared instead of one component, you just measure total angular momentum. You find that it's always a certain number, okay, for YLM. Okay. So because all different YLM actually have the same eigenvalues for L squared, okay. So no matter which state you are measuring on, you always got the certain values of this L squared, okay. But if you measure LZ or LX or LY or L east, L west, L left, L right, no matter which direction you choose to measure, you always got a certain number, integer number m times h bar, okay, randomly. Right. And then the state will be you can choose that axis as a z-axis, and then choose the angle phi defined about that axis. Okay, that will be the state. Right. So I can make this statement. So after measure LM, sorry, that's defined as m dot L, right? You measure this fraction, you got the results m h bar, okay, and the state, the original state will becomes YLM. Now it's theta prime, phi prime, and this one is phi prime, and this angle is theta prime. So you just got a new state, and this new state now is defined about this axis. You can call this one z prime, okay. Right. So after the measurement, the state will be just you do the measurement on this direction. You got a state run out of the m h bar. So that means you already choose this axis as a z-axis. Okay, so that's the answer to your question. So you don't have to decide which one is axis. It really depends on where you choose to measure the angular momentum, right? If you measure in this direction and this direction is z, and you should measure another direction, the other direction is z. Okay, just a convention. All right. Any other questions?